So moving on to the book, looking at chapter 13 this time around, the focus on this one was building a segmentation model and understanding some of the metrics and some of the surrounding things that we need to do to get it into the right format to actually do that. So in the first section, they were kind of talking about, well, what actually is segmentation? Why would we want to do this? We already have a model that can tell nodule, not a nodule. And the function of this segmentation model is intended to locate exactly sections where the nodules might be. And so the big thing with segmentation is you're just doing a prediction actually at the pixel level rather than at the patch or image level. And so along with this, we need to change a lot of things. So our input pipeline has to change. We're going to be looking at a different target. We're going to use a different kind of model. We'll have a different training objective because we can't just use the same binary cross entropy necessarily. And then they also introduced the UNet model that we'll talk about a little bit in more detail later. They mentioned one existing UNet implementation, and that's different than the one that I've used in the past. This one that I have here, I highly recommend it. Used it in a lot of Kaggle competitions and stuff. Just wanted to point out its existence because it's very flexible and you don't actually have to code up all of it, because it's a little bit annoying when you code a model from scratch, specifically the segmentation models, the UNets. They're a little bit trickier to piece together because you need a lot of matching dimensions and layer sizes and stuff like that. So if you want a good starter implementation, here's another one. They showed another one in the book. I just thought I'd bring that one up too. And so actually moving on to 13.2, looking at the different kinds of segmentation, there's semantic segmentation, which is the one that we're interested in, which is basically you're outputting an image, and that new image is going to have ones where there's the things you're interested in and zeros when there's not the things you're interested in. And you can do that for multiple layers. So you can output multiple images at a time. So you could have one layer that detects where the dogs are, one layer that detects where the cat pixels are, and so forth. You can have as many as you want. And typically the output is the same resolution as what your input was. So if you have a 500 by 500 input, then you'll have a 500 by 500 output. And then you can look at those together and say, okay, here's the pixels where the dog is, here's the pixels where the cats were, and so forth. And then a different variation on segmentation is instance segmentation, where instead of just trying to say, here's the pixels where cats were present, I want to label, here's cat 1, here's cat 2, here's cat 3, and then it will actually label all of those separately. It's still at the pixel level, but it's going to tell you that there are different instances of the same object potentially. And so that can span multiple instances of one object, but it can also span across cats and dogs and multiple other things, just to point that out too. And then there's object detection, and the difference there is it's just drawing a bounding box typically. So maybe it's not actually important which pixels specifically down to that granular level. Maybe you just generally need to say there's a cat in this region, dog in this region. And with that, you can pretty easily say, here's 8 in this picture of this kind and 3 of that kind, and so on. Is generally pretty good for counting things. So Hobbes a while ago was talking about a process where he was trying to count the number of flies. And so object detection would probably be what he uses there. Before I move on to 13.3, any questions on these first two sections?
Could you maybe go into a little bit about the differences in the labeling of those? So if we're doing like semantic segmentation or instance segmentation, generally versus like object detection, right? Object detection, you'll get the bounding box coordinates, but with the others, we're going to get the mask information, right? And if you're annotating these with the generally available tools, is that the only option for instance segmentation and semantic segmentation, is to get those binary mask information rather than any specific types of coordinates for the boundaries of those labeled in the semantic and segmentation, instance segmentation?
Yeah, typically the way it works on the labeling process is you need to have someone actually go through and basically run it like a coloring book, where they're just saying, I'm going to scratch off the area where the car is, or whatever else. One of the local companies, Vivu mentioned them earlier, Comma AI, they have a project where they basically open sourced a little coloring thing where they say, we've got 10,000 different car scenes and we want you to color in all of the sections where there's cars as green and pedestrians as red, and whatever else. And it's just, they've created a GUI and you kind of just have to sit there and do the coloring book thing. There might be some better operation to do that, but I haven't seen one.
You can actually make models to like try to do that stuff. Typically they're not that great, but depending on how well you make it, they can do those tasks pretty well. There's some companies that you can reach out to that do it. Scale AI is a big one. So they have their own pipelines where you send them all your data and they have their own models that'll like do image segmentation or labeling or whatever. So depending on what your needs are, there are like options out there. There's also for like text, there are other models that'll just do like POS tagging and they'll just spit out like, oh, these are nouns, verbs and stuff. But for images and stuff, there are companies that'll like, they have their own model. So if you don't have something that's like, you don't need like the best accuracy, or just trying to like mess around with a project, you can like go that route too.
Yeah, like for instance, if you're talking about labeling like flies, right, or being able to detect flies. So if there's one fly next to another fly, and you're using instance segmentation to try to distinguish those, or you might not be able to distinguish one from the other, right? Or like the actual coordinates of where one fly begins and the other fly.
Yeah, that's like its whole area of research. So like if you think with like cars, like they need to know where a stop sign is and like where the lane lines are, like where a stop line is, where a red light line is. So you can work on models that'll do that, and based on the accuracy you need, if you're just working on like a simple fun project, you might want to just reach out to a company like Scale and like be like, they probably have a free trial. Can you like label these 1,000 images based on where the flies are? They'll give you a decent result. If you need something with pinpoint accuracy, like you want to know where stop signs are and where you stop, where the exact line is, like something like Tesla needs to do, they're going to work a lot harder on that problem, So there's just different routes you can go about doing that. But most of that stuff is done with CNNs. I see some stuff with transformers popping up, but yeah, it's like its whole field.
Mm-hmm.
So in terms of just like the type of vision problem, the way I think of it is, if you're doing image classification, you're spitting out one label for the whole image. If you do semantic segmentation or instance segmentation, basically what you're doing is you're spitting out a label for every single pixel.
Right.
So in semantic segmentation, like you may do like cat, dog, background, whatever. And then as Ryan said, if you're doing instance segmentation, then you wouldn't just do cat, dog, you would do cat 1, cat 2, cat 3, dog 1, dog 2, dog 3, background.
Mm-hmm.
And so I haven't spent a lot of time with instance segmentation or object detection, but it gets tricky because, like, a priori, what's the maximum number of cats you allow in a single picture, right? So if you're going to allow 20 cats, then you need to be able to have those 20 classes, cat 1 through cat 20. Same thing for object detection. You need to have up to 20 bounding boxes that all are just for cats.
I mean, one big bang for the buck in semantic segmentation, at least in the healthcare industry, is you get measurements. And so if you're looking like at the heart and you're seeing the left ventricle, you can actually get the size of the left ventricle by semantic segmentation. Or if you're looking for a liver and you want to see the size of the liver or a bladder, it's very good for doing things like that, because not only do you get where it's located, but you also get sizes and dimensions and things like that. You can calculate with it.
Yeah, and to be clear, the segmentation is not doing it. It's once you take the output of the
Yes.
segmentation, then people can go and they can say, what's
That's
the
right.
diameter of this and the
Yeah,
length of
and
that.
you can count pixels and things like that. Yeah.
Right. But then if there's two bladders that are next to each other, they just kind of
Yeah.
morph into one. So you kind of lose a little perspective on.
Yeah, that's right.
Yes, that is the weakness of just plain old semantic segmentation. If you were whatever, if it thinks there's two left ventricles, then you're just going to see, you know, whatever, right? A figure 8, and the computer's not going to know how to measure that.
Okay, can we please get the link to the segmentation GitHub page, which Ryan showed on the same page where all the text? Yeah, here.
Yeah, I'll share this.
And then I can link all the notes afterwards too.
So what I was just scrolling through, so this is related to the labeling process. 2 of the previous competitions I've done have been on semantic segmentation, and it's kind of interesting because in both of them, they've actually kind of hidden their labeling process inside of websites and games. So in this Understanding Clouds one, what they did is they basically took their system to some sort of, I don't know the formal term for it, basically a weather conference. And they got a bunch of meteorologists or whatever to go through these labels and label the clouds with their various different classifications. And so they just gave them a web GUI and they crowdsourced it and they said, here's what this kind of cloud looks like, here's what this other kind of cloud looks like. And then they just basically said, here, all of you people just roughly give us a label for these things. And what they did is they took the combination of multiple people labeling the same image in order to build it into a semantic segmentation map, because they know that people are generally going to not be very precise, but across several different labels, it should, in theory, focus in on the right thing. And then in this Human Protein Atlas one, what they did is they hid it inside of the EVE Online video game, which was kind of interesting. It's a space-based game, and they basically posed it as a mini game where people are trying to discover extraterrestrial something. And so people would just sit there and play the game, and they think they're playing some game, but they're actually doing the labeling process for this. So they were able to get a lot of high quality labels here. So the process of getting labels is kind of interesting, and you have to be pretty creative. There's a whole paper written on their whole data collection process that was kind of interesting. So moving on to 13.3, semantic segmentation for pixel classification. So in our previous approaches, we learned about convolutions and max pooling and how we can piece all of those together. And what that's really doing is it's taking our 224 by 224 by 3 image, and it's eventually reducing it down to a single bit of information, a single pixel's worth, basically saying cat or not a cat, or dog or not a dog. or a thousand ways if we're doing multi-classification. And so in semantic segmentation, we have a much sparser space because we still have 224 by 224 as our final output, but then we have the number of classes. So we have a much bigger space there. And so one of the problems is we typically want the output to be the same input, the same as the input. And so in order to solve that, we can't necessarily just do convolutions and max pooling. Those were great because they increased our receptive field. So you could see very large patterns across the entire image. But the problem is every time you do that convolution and max pooling pairing, you're losing some precision. So the max pooling is reducing the resolution by 2 and then 2 and then 2. And then at the final layer, you might have a very small 4x4 image. And if you're trying to output something, then you only have a very tiny amount of precision on the pixel level, actually. And so what people have come up with in terms of UNets is it's probably easiest if I pull up the diagram, actually. You have this U diagram though, and basically what it's showing is the typical path of condensing it down to some simple vector, but then instead of actually, so looking through this path, we've got the one path that is condensing the information down to this vector. This whole branch would typically then, we would put some dense layers here, and then we would say, okay, now make some classification off of this. But what we want to do with the UNet is then rebuild this into close to the original resolution. In this example, they had a smaller resolution, but most of the time you'll want the same resolution. Then you take this condensed information and then you try to build that map back up. But like we were saying, the convolution max pooling is reducing the precision. So in theory, even once you do all of this upsampling, it's going to be very imprecise. And so what people figured out is you can do these skip connections, which is basically saying, let's take the original image and pass it over here. And then this condensed information over here can be basically painted on top of this original image and coincide with the actual broader information from the original image. And so that's kind of the intuition behind the UNet, and it's proven to be really successful. There's other variations, but the UNet and the UNet++ has shown in 3 or 4 competitions that I've been in to be very useful. People haven't really been able to beat it. Actually, any questions on this diagram before I go back to the notes?
Hey, Ryan, are there any other relatively big architectural designs for segmentation other than the UNet?
So I learned about most of these from the segmentation models package. And so they show that there's 7 different model architectures, and then you can plug in 57 different encoders. So we were talking about pre-trained models before. You can plug in all of your ResNets and efficient nets and VGG and AlexNet as different encoders. And then there's 7 different model architectures, and that includes all of these. And so UNet, in my experience, has been the most successful, but there's also promising results from LinkNet and FPN and all of those. I've tried these on various different occasions, and typically UNet has been the best for me. But you can see, this is the reason I like this this library, is you can basically plug in any of these on top of this. And so you can do a lot of different studies of the different models and architectures.
Nice. Thanks, Ryan.
Yeah. And this is actually this, I don't know how to say his real name, but Quibvel. He's done very well in a lot of Kaggle competitions, so he's kind of proven that his library is a good one to use. He's got correct implementations of all of the algorithms. Yeah, so some variations use upsampling, which is basically, let's say we've got a 16 by 16 image and then we want to upsample it to be 32 by 32. And so you're just basically doubling the size of all of the pixels. But that's been shown to not necessarily be optimal. It might be cheap to apply that operation, but a more performant in accuracy sense option is to do the transpose convolution, which is basically just the opposite of our normal convolution. And so you might see some implementations that have upsampling, some implementations that have transpose convolutions. And this is just an operation that you can find within PyTorch if you ever need to do that. A long time ago, when I was doing the first semantic segmentation competition, I was trying to code it all up from scratch, and it is very difficult in terms of all of the sizes and stuff. I am very grateful for the existing packages, because calculating out all of the sizes and making sure, oh, this skip connection has to match the resolution over here, and this one lost a pixel because of padding, but then it gained a pixel because of upsampling. There's just a lot of different moving parts. So highly recommend using an existing implementation if you can. So on 13.4, updating the model for segmentation, they basically just gave the code details and said, we're adding in batch norms so we don't have to normalize the data on the way in. And then they're using the pre-existing implementation of UNet. So if you look at their code, there's not actually a whole lot that they're doing there. They're just borrowing an implementation, and they're just saying, I'm going to define this UNet with a certain size of dimensions and a certain number of outputs, and they don't have to do a whole ton of coding there. And then they add on a sigmoid layer to make it so that they can have 0 to 1 for the different outputs. And then moving on to 13.5, they started explaining what do they actually need to do in order to update things to be appropriate for the segmentation task. So one of the things they mentioned is that you need the specific dimensions. That was something that I was mentioning too. It depends exactly what implementation you're using, but typically I've seen that people recommend that you just have your images be some factor of 32. So if you want, you can make it 128 by 128 or something like that. The details just depend on the implementation, but you have to be a little bit careful with the sizing because of all of that stuff in terms of there's padding and upsampling, and you might lose a pixel here and you might gain a pixel there, and you need to make sure that everything correctly stacks on top of each other when you're doing those skip connections. So the input dimension matters, and then the actual implementation of everything matters too. So you might end up with a headache, and you might be able to solve it by just changing the pixel size by 1 or something like that. So just something to be aware of. One of the things they highlighted is that UNets can be super memory hungry. So typically with the CNN, we might have a couple convolutional layers, and then we very rapidly do max pooling. So if we have a 576 by 576 image, and we do 64 convolutions on top of it, and our output is 576 by 576 by 64, that's completely massive. But if we start doing max pooling very early on in that process, we might be able to reduce that resolution by half, but actually reduce it even more than that, because we're doing less computation on all of the convolutions. So just in general, you have to know that UNets use up a lot of memory because you're doing an output and potentially an input that's a very high resolution. One thing that's nice about UNets is you can potentially apply it to different resolutions down the line. So they showed that we're going to be training on 64 by 64 images, but then they're applying it to the full size images, which works reasonably well. It doesn't really matter what input size you're doing. If you do the same on other kinds of models, you'll probably have some pretty large degradation in your quality, but on UNets it does reasonably well because you're doing that mapping from the higher resolution to start with. One of the things I was a little bit fuzzy on is they had this whole section on how they were actually deriving the mask out of the original labels. And so they were doing some sort of search across the density in order to make sure which pixels were nodules and not nodules. I haven't had to do that in the past. I wasn't entirely following what they were doing in the past. I've just kind of been given the labels. I think that that was just specific to this use case and the way that the labels were given.
Yeah, I mean, I can jump in if you want, just do a real quick. So basically, they were pointing out, like all too often in the real world, you want targets so that you can do your supervised learning. And in this case, if you have a 572 by 572 image, you would want, again, every single pixel tagged as whether it's nodule candidate or not. But that's not what the label data was. The label data was just some center points. So then what they did is they looked at each center point and then they just said the bright white, the high density pixels that are above this cutoff that they arbitrarily chose, we're going to consider that part of a nodule or not. And so then they just went left and right and they said, what's the first low density pixel I run into, assuming that the nodules are round. And then they went up, down, and they said, what's the first low density pixel that I find? And typically those values would be within 1 pixel of each other because, again, it's supposed to be round. Okay, so then they said within that square or maybe slightly rectangle, if they're off by 1, then we're just going to we're going to label every high density pixel as nodule and every low density pixel as background.
Mm-hmm.
And then in the book, they actually showed an example where there was a nodule really close to the wall of something or whatever. And if you look closely, what you'll see is the circle is colored as nodule. Yeah, so not the one in the middle, but the one to the lower right. But then you'll also see the tiny bottom right corner of that rectangle included a couple bright white labeled nodule pixels incorrectly down there. So when we train on this, it's actually going to incorrectly give you negative feedback if you say that that's part of the lung that's not a nodule, because it's going to say, nope, those whatever 6 pixels in the corner there, those are actually. But in the grand scheme of things, they said, I mean, in a perfect world, yes, but for the case of just a book and showing you that it learns, it'll still learn despite a couple of those bad labels.
Mm. Yeah, thanks. That makes sense. So they made the masks using that process, and then they decided to do this interesting technique where they're basically pulling in the 96 by 96 areas around nodules, and then within that, they're taking random crops. So they're basically saying, here's the region where the nodule is, and then I'm going to grab random subregions and have the model train on those subregions. And it's kind of showing it multiple different variations on the same input, basically. And I think that helps them get additional samples because the nodules are so rare in this instance. And it also helps prevent the massive class imbalance that we've come across here, where the majority of pixels are not nodules, and we're mostly interested in the ones that are actually nodules. One of the tricks that they showed was that I thought was kind of interesting is you can make a model that is essentially just an augmenter. And so they built this new model class, and all it's really doing is it has a few different augmentations built into it. So if they want to do some rotation, if they want to do some, I forgot exactly the operations they did, but you can code in various different operations inside of the augmentation, and then you can just have one model pass into the other, and then your new input is going to be augmented. And that helps you out because it will automatically be pushed to GPU. Basically, you don't have to do anything complicated where you're constantly going back and forth from CPU and GPU. So,
hey, Ryan.
Yeah.
I was curious because, you know, I've seen lots of augmentations, and you can say, again, shift it a couple pixels up, down, left, right, flip it, you know, whatever. But in their code, it looked to me like they were picking a random rotation, like between 0 and 360 degrees. And so I was wondering, if you rotate a square 45 degrees, don't you have problems like with what to put in the corners?
Yeah, so that's, they typically just give you some parameter to say fill with zeros, fill with 255, fill with whatever. But yeah, you will end up with just blank regions potentially.
Yeah. I don't think they explicitly mentioned it, but in this case, because the background is like zeros, so when they did their matrix multiply implementation of rotation, then you're just going to get zeros, I think, in the corners, because there's very few, you know, cells that are contributing towards the product and sum in those corners, you know. So you're going to tend to mostly just have zeros. But in this case, that's okay because 0 would be non-nodule.
Yeah.
But I felt that they just kind of skipped right over that, which if you were doing something else like dogs and cats, then you might not be as easily able to rotate it 45 degrees and not care what the corners look like.
Yeah. Rotations were something that I spent a lot of extra time thinking about on the lift competition because had to figure out how to make everything line up. And I haven't really thought about it, but you're actually rotating around the center of the image. I had to spend a little bit extra time realizing that you're not rotating around a corner or something like that. Just understanding kind of the I don't know the proper term, but the focal point of your rotation is actually kind of meaningful too. So then they showed the process of updating the training script. So they said, let's make our augmentation model, let's make our UNet model, build the two of those with the parameters that we want. And then they plugged in Atom instead of SGD that they've been using for the past couple chapters, probably just to speed up convergence a little bit. One of the things they laid out is that we probably want a different loss than what we've been using now that we're doing segmentation instead of classification. And so they laid out this dice loss. And what this dice loss is doing is it's basically taking the pixel level F1 and then it's averaging it across the entire image. So you're kind of doing the same thing if you're measuring true positives and false negatives and true negatives, and then you're aggregating that across the entire image in order to get your F1 score. So if you have a totally blank image and you have all negative examples, then you get an F1 score for that image of 1. And if you have a full mask, so it's all ones, and you guess all ones, then you also get 1. But if you have a blank mask of all zeros, so there was no nodules at all, but you guess a single pixel of nodule, then you end up getting a 0 actually. If I'm posing that correctly, I'd have to think about that a little bit. But that's been something that's been pointed out in past competitions where the dice loss is actually a bit noisy in that regard, where a false positive can be brutally penalized. And there's also other variations. So there's IOU, the intersection over union. And there's various other options. I just wanted to point out people have tried various different things in this regard. Sometimes it's best to just keep binary cross entropy. Sometimes dice loss works. There's this other one called Lavaz. There's focal loss. There's a whole bunch of options here. And it kind of just depends on exactly what your class imbalance is and what your overall goal is, because sometimes having false positives isn't really that painful for your use case. Sometimes it's catastrophic. And so you kind of want to line up with what you actually care about and make sure your loss corresponds with that. One of the things they showed was the weighting. So along that line of different objectives can give you different end results. You can also just manually change the weighting. So you say, I really care about catching all positive cases because in this scenario, we're using this as a pre-filtering step potentially for the binary classifier later. So it's probably better for us to pass more to the binary classifier after, because we don't want to miss things in the segmentation step. It's probably better for those to get filtered by the classification step after. Another trick that they showed was loading images into TensorBoard with log images. So that's really useful if you ever have your prediction mask and you want to compare that to the label mask. You can just periodically load some images into there and then do side-by-side comparison and see exactly how it's doing qualitatively. Because you probably have your metrics like your F1 and your dice and your precision and recall and that stuff. But it's also interesting sometimes to manually look at the outputs and see, oh, it seems to be missing the cases where the nodule is very small or something like that. Actually looking and seeing the results is typically good for troubleshooting and building a better model in the end. They showed saving the model. We've done this a few times. That wasn't that unique, but basically they showed we can plug away just the parameters and we can plug away the optimizer as well. And then we can just load that in later. And another trick that they showed there was that you can capture the hash of the model definition and then compare it later to make sure that your hash matches between them, so you don't actually load weights into a model that isn't really the one you wanted. I haven't necessarily used that method in the past. I feel like that's a little bit awkward. I feel like that solution isn't fully fleshed out yet, but I haven't seen something better necessarily. So if that's what they're recommending, I guess we can go with that. It just seems a little bit risky to have your parameters separated from your model definition and just hope that your code on the other end matches it. But in theory, if you're organized, you can just keep track of that. So in the final section, the results, they showed that
Ryan,
yeah.
Before you move on, I wanted to go back a little bit. When they talked about the weighting, if I remember right, the authors said it's a good thing we're using Atom because the way we're weighting it, this would just break SGD. And I wasn't sure why something like that would break SGD. I mean, like maybe you need a slightly lower learning rate, but I don't know. Did you think about that at all?
Um, I don't really know why that would be. I would have to look back at their claim. Maybe there's something to do with Atom and its momentum being able to get you over certain um, difficult regions, but I don't know exactly why that would be.
Mm-hmm. Yeah, I mean, that was just one of like, I mean, you've pointed out a bunch of them, but like, I was kind of present to like, wow, so if you were sort of looking at this realistically and not just here's my presentation in the book of what works, right? There's probably at least like 20 dead ends.
Mm-hmm. Yeah.
And so it was actually for me, it was a little bit intimidating. It's like, oh, well, we tried training it on the full size images and that didn't work. And then we tried doing this and, and if we'd done this, then that would have run out of memory. And if we did that, that wouldn't have worked. And if we did that, maybe it would have worked, but it would have taken forever.
Mm.
So I don't know. I think it's good that they're trying to show realism, but it was for me a little intimidating.
Yeah. I think that's part of the difficulty of machine learning, though, is every problem is different and you need to kind of make alterations and customize and see what works and see what fails. So they're kind of holding our hands, but this is realistically the kind of problems that you're going to run into, and it's good that they're at least mentioning them.
Yeah, I wouldn't want them not to mention it. It's just, I don't know. Again, this is a book about learning PyTorch. It's not necessarily meant to teach you all of data science, but it's just, there's a bunch of things in there where it's just sort of like, okay, I guess, you said so. I'm just along for the ride.
Yeah, that's part of what makes Kaggle competitions attractive to me, though, is I get to see how other people fill these gaps and say, oh, I was seeing this problem, so I did this. That didn't work. Okay, now I'm going to try this other thing. And across many competitions, I've been exposed to the various different techniques to solve the different problems and how they apply in different domains and stuff. So that's what's been positive for me on Kaggle. So just wrapping up the results section, they basically showed our training is looking pretty good. Our metrics we want to go up are going up. Our metrics we want to go down are going down. But then looking at the validation set, it looks like somewhere between 5 and 10 epochs, it ends up overfitting and the metrics are not necessarily going in the direction we want. So I'm assuming in the next chapter or in some future time, they'll probably show, well, here's how we prevent overfitting. We add some additional augmentation step. We do some different pre-processing, or we format it in a different way. And then they can make something that's useful for the later binary classification model. So that's chapter 13. Any questions on any of this stuff?
So I didn't fiddle with the code much at all this week, to be honest. But I will share that in terms of just being comfortable with PyTorch, I am starting to feel pretty comfortable. Like they had that one thing you mentioned where it's like, well, we could do augmentations just as a custom function where we input a tensor and we output a tensor, right? But they're like, but hey, that's basically what a unit does. So why don't we just subclass that? And we'll just build our own custom unit. And instead of, doing something like a CNN or whatever, it's just gonna, do a random number generator and decide if we're gonna flip, decide if we're gonna rotate, whatever. And I was like, okay, this code actually makes perfect sense to me now.
Yeah. Just good.
Anybody else have any questions, comments, things you like, didn't like?
If that's all we have for the chapter, maybe we can do some breakout rooms if anyone's interested. I don't necessarily have anything else to discuss.
Yep. I'm just showing again if anybody joined in the middle and wasn't here at the beginning. So this is our plan for the upcoming schedule. So I haven't looked exactly to see when Thanksgiving falls, but naturally the next book would start, if we just keep going on this pace, would start November 21. And then what Ryan and I have been talking about is that we do not have to heavily read the different parts of the data intensive applications book consecutively. We can go 3 weeks, and then we can, intersperse some stuff on transformers, and then we can, go another week, and then we can have, other topics. So, so by no means am I necessarily thinking that we're just going to go straight through on the next book. The chapters don't seem to as heavily be linear and build on each other. So just wanted to share that again. All right.
I have a question on segmentation. So let's say I want to do segmentation, and then I want to do classification, like let's say in this case with nodules or some other problem. Like in general, would the same type of networks work well for segmentation and classification? Let's say you make a UNet from like ResNet. Would like both of them work equally well?
Yeah, so in the past, we did a competition where we were looking at pneumothorax scans. And so in some ways, it was a little bit similar to this, where we were given a X-ray or some sort of scan. I forgot exactly what it was. But what ended up being successful was we have the UNet try to create the best mask possible. But then at the bottleneck of the UNet, we have it have a branch that just directly tries to do a classification of, does this person have pneumothorax or not? And then we use one to filter the other, basically. So we have on the one side, we have, it's trying to guess pneumothorax, not pneumothorax. If it guesses pneumothorax, then we pass out the mask that was generated from the other branch of the UNet. But if it's deemed that they don't have pneumothorax, then we just zero out the whole mask. And so in that scenario, you can do both off of the same neural network architecture and just put the associated tasks, the classification and the segmentation on the corresponding pieces of the network.
Oh, that's interesting. I was actually asking like a simpler question. So let's say something works well for classification. Would the same network, like type of network, be a good base for UNet for this problem?
Yeah.
And the other question would be like basically probably the same augmentations would work if it's the same problem.
Yeah, typically. So if you find that a ResNet 50 works well for a classification task, it would typically also work well for segmentation as well. So what people do, let me share my screen again. What people do is in this scenario, they leave it kind of vanilla, where they're just saying, we're going to do this reduction down this entire path, and then we'll pass it over to this right side here. But what you can do is you can inject your ResNet 18 or whatever, and you can say, okay, at this point, I'm going to take this 280 by 280 image, and I'm going to pass that into a ResNet 18, and then it's going to create this encoding for me. And so you can reuse those ResNet 18 pre-trained weights or whatever you want. You can plug that in. And so that's what was being shown on here. You can plug in all of these things, and then it will basically link into the various different networks, and those will typically be successful.
Is that a more efficient approach in terms of performance or time it takes if you use a pre-trained ResNet? Does it make a difference?
So it was kind of what's, I don't know if you were on when Stephen was talking about this earlier, but typically with the pre-trained weights, you'll get better results faster. Whether or not it gets you better results in the long term after you train for a long time is a little bit unclear. But typically you'll get better results from starting from pre-trained.
Okay, got it.
Yeah.
All right, if there's no other questions, then I think what I'm gonna do is I'm gonna open up 2 breakout rooms and just give a chance for people to meet other people. You can ask questions, you can talk about projects or ideas that you have, listen to what other people are doing. I hear there's this election coming up in a week. And then I know that the pop-ups are not very easy to see, so I'll try and put, multiple up, but, we do have enough time to potentially switch up the breakouts if people are hanging out. If a few people have to go, you've got other plans, we drop out, then we might just have enough people just go back into one big room. But right now, I'm just randomly assigning dropouts, the breakouts, and let's give this a shot. Come on, you can do it. All right, so you should see an invitation to join your breakout room now.
Hello.
Hi.
I like your background.
How's everyone's week been?
I've been busy. One of the things that I'm supposed to help do is advise our customers on if there are sort of, say, a lot of COVID positives at their company, And so with the numbers going up the last few weeks, it means that there's more and more questions about, hey, there's some people who are positive in this location in Iowa. Like, should we be worried? Do we, what do you recommend we do now? So that's been